Hey, what's up? Um, so, good news, bad news situation. If you watched the last video, you would notice there was no sound to it. I didn't realize that until just now. So, both sad that there was no sound and equally sad that no one let me know until I was able to discover it on my own today, over a week from when I posted it. Nevertheless, really, if you just followed along, which would be far more boring than just listening. I mean, I say far more boring for some of you who have your own opinion than if you just watched it. Anyway, you still could get a lot from it, and really, it's kind of a perusing. It's me just talking over the content that appear in the slides as it is. So um, I'm going to voice it over. I'm going to leave it up until I get that fixed, but I'm going to voice it over later after I get this video done, video 2, and we'll go from there. So without further ado, we're going to start off with Solutions Section 2, Part 2, if you will, Solutions 2 of Night Chemistry, and we're going to get straight into the topic of questions. So Solutions 2, Night Chemistry. Here we go. So I'll bring you to really, this is November 23rd. This was the Monday before Thanksgiving. The do now slide. Now, Monday and Tuesday were mostly monopolized by two things: slime making and ice cream making. Now, both those were at the end of the period. That way, you had to work for it a little bit, and there was mostly independent work time. I would say that I did not do a good job of cheerleading the work time very well, because I was hoping you would take responsibility. The students would take responsibility for their own time and realize that these are important workday times. And that was still when the impression was that the exam would be on Tuesday when they came back. They took, a lot of them took for granted their memory and how much they would remember, so they sacrificed a lot of that time, which was their own prerogative, unfortunately, for better or for worse. Nevertheless, they had to do some big time catch up work and come back on the 30th, first day back Monday, and then today Tuesday. So I extended the test one more day. I wasn't going to do another day because of memory, whatever. That's not up to me. I put in place a lot of opportunities. Some of them were scoffed at or sacrificed at the altar of self-indulgence or selfishness. Nevertheless, we're going to move past that. Exam is Tuesday. This is 12/2. This video might get posted today, 12/1. My goal is to do it by today, but other mitigating circumstances could play a part. Nevertheless, we're just going to dive right in and get to the slides. We're going to see what we can accomplish verbally here as much as we can. And then we'll try to do some practice. If time allows, I'll post a separate video of me accomplishing some practice problems. Otherwise, I'll post at least the slides from in class that shows stepwise solving of some of the more difficult problems. So once again, stay tuned for all that. And here we go. We're just going to dive right into the situation. So biggest thing here is dissolving process. Focusing on that. That's a big key. That's a key essay question for the exam. Also understanding the factors that affect solubility or the solvation process. You need to use the term solvation and dissociation because those are part of the standard as well. And then, of course, we have this notion. Anyway, so we have the dissolving process. And then we have a lot of concentration calculations going on. That's why the next problem is the equation for molality, probably the second most important equation in solutions concentration calculations. Anyway, we went over those equations. I presented all the equations to students so that way they'd have those for the work days. I taught those on the Friday of November 20th. This day 2 of solutions unit, that is, and then day 3 and 4 were all work days, slime making, ice cream days, whatever. Those may not be necessarily the way we do it in the future. So still, what comes next? Molality and problem solving. So let's just get straight to it. Other solution concentrations. I will do it in a second. All right, so when we talk about solutions, we want to specify mostly about the composition of the solute, i.e. the concentration of the solution. There are 5 major categories that we explore in this unit for solutions. Though the 6th one is actually the second most important one. That's molality. Oh, excuse me, 5 molality. 4 is included as molality. We have percent by volume, by mass, by weight. Those can be given to you. They're kind of applicable in multiple circumstances. I posted the formulas that we have from class, and I write this one as percent by blank because it always equals mole or blank solute over total blank. Whatever the blank is, volume, mass, weight, fills in all those areas depending on the percent. And you're going to actually see that here in a second. Molarity we already talked about on the last video. I'm sorry, I already mentioned on the last video. It will be voiced over in the next video, but as best as possible. Anyway, molarity is the most important concentration one. We have an entire worksheet dedicated almost solely to it. Mole fraction, it's a mole over part. Oh, it's moles part of the total moles, basically, of the solution. Molarity was moles per liter. That's a part over the whole. Percent is naturally a part over a whole, sorry. Molality is one part to another part. Usually it's solute to solvent, not usually. It is solute to solvent. We'll explore that in a second. Normality is really used for acids in buying reagents from suppliers. Is how it can often be presented. But it's just a multiplication, a multiplier of the molarity times by the number of H's. So normality, just molarity times the number of hydrogens in the chemical compound. So let's keep going. Percent by mass. It's the mass of the solute divided by the mass of the solution. So percent mass, or weight in this case, or in some cases it's mass of the solute over the mass of the total solution, or the total mass of the solution. Times 100 gets us into a percent. We would just move the decimal. So here's the sample problem. Determine the percent composition by mass of 100 grams. 100 grams of salt solution containing 20 grams of salt. 20 grams over the 100 times 100 is a 20% NaCl solution. Typically, aqueous solutions, which means water is the solvent, they're presented as percents. Just how it goes. Let me move me real quick. All right, good. Percent by volume, it's the same thing. It's just volume of the solute over the volume of the solution. Now, the general premise with all of these equations, and the ones I posted as a video or as a picture on Google Classroom, is that you want to pick out this equation and either use it to pull out data or else use data from the problem and then convert as needed to fit it into the equation, the places, plug it into the equation, and solve for it from there. So for what it's worth. So another example here, we have 70% VV rubbing alcohol would be prepared by taking 700 milliliters of isopropyl alcohol and adding enough water to get 1,000 milliliters of solution. That way it's 700 over 1,000 is 70%. And it won't necessarily be 300 milliliters because the density is a little bit different. Anyway, mole fraction is yet another way to look at the composition of solute. This takes the moles of one of the components of a solution. Now, this is more prominent for solutions that have multiple components. There are multiple solutes with a solvent. And so the solvent has a plurality maybe, or maybe a majority of the composition. Anyway, it's where you do the moles of one part over the total moles, so the addition of all the total moles. And this is given to us by an X, and the subscript is the mole fraction in question. So what are the mole fractions of the components of solution when you have 92 grams of glycerol mixed with 90 grams of water? So we convert our 90 grams of water into 5 moles, 92 grams of glycerol into 1 mole of glycerol. So the total moles would be 5 and 1, 6 total. The X, or mole fraction of water, subscript water, means that's the mole fraction of water, is the moles of water over the total moles, 0.833. Notice we leave them as fractions, or as decimals, which are just another representation of a fraction. The mole fraction of glycerol is the moles of glycerol over the total moles, 0.167. Once again, we took numbers the problem gave, 90 grams of water, 92 grams of glycerol, converted them to moles so they fit the equation of mole fraction. Plug them into the equation, part over total, and you turn out an answer for each of them. Notice the idea is that mole fractions all add up to 1. Just like all percents add up to 100, all mole fractions add up to 1. Molality is the second most important concentration calculation behind molarity. This is given to us as a lowercase m. I know I capitalized the word molality because it's just a proper noun in this case. It may not even be a proper noun. Anyway, it's the number of moles of solute. Stop, pause, and read the slide if you'd like to, or go back and read the other slides for that matter, or go back and read the other slides from, or this slide from the slides presentation. Molality is given to us by a lowercase m. This is to contrast against the uppercase m of molarity. Molality is number of moles of solute. That's similar to molarity, but molality is moles of solute over kilograms of solvent. So this is now a ratio of one part to another part, a ratio of the solute amount to an amount or quantity of solvent. It's always moles per kilogram. That's our shorthand, is we'll just do mole over kg. But we still have to be distinct in understanding that we're talking about kilograms of solvent. I'm so distinct there because molarity relates moles over liters of the whole total solution. This moles solute over the kilograms of the solvent. It's a direct ratio. And we practice this pretty good as well. I show you this again. I give you a little stepwise worksheet that acts like notes, and we go with it from there. Cool. So in this example problem was the molality of the solution, where you have 10 grams NaOH in 500 grams of water. Immediately I pull out from the problem that we have 10 grams NaOH. That is a quantity of the solute, because water is almost always the solvent. And that's just the easiest way to go with it. So 10 grams of NaOH, I need to make that moles of solute, convert those quantities. And then 500 grams of water, I need to make that. That is the amount of solvent, so that at least makes it easy. It's not buried in the amount of solution. I need to make that into kilograms of solvent, and I can plug it into the equation. So let's go. 10 grams of NaOH divided by the molar mass of NaOH gets us the moles, 0.25 moles of NaOH. 500 grams of water is divided by 1,000 grams to get a kilogram, makes half a kilogram of water. Molality is moles over kilograms. Divided, you get 0.05 moles per 1 kilogram. Nope, that's not right. It's 0.5 lowercase m, 0.5 molar. I don't know what this step is about, but that's incorrect. So let me mark it out just for now. This is us right here, because 0.25 over 0.5. Check it and see yourself, and you'll see that's a good work right there. Okay, remember molarity, moles of solute over liters of solvent. Wait a minute, what? That's an issue. Sorry, that slide was broken somehow. Anyway, molarity is moles of solute over liters of solution. So what is the molarity of a solution? Practice run here. When water is added to 11 grams of calcium chloride, which I would measure out first, put in the bottom of the container, add enough water to get to 100 milliliters, because I don't want to add 100 milliliters of water because that's the amount of solvent. I want to add enough water to get to 100 milliliters because I'm accounting for the volume taken up by the 11 grams. Anyway, I got to convert grams to moles. So I divide by the molar mass and get moles. Milliliters into liters, because it's got to be liters of solution. Molarity is moles over liters, which is 1 molar in this scenario. Normality is the last little thing. It's a gram equivalent weight of the solute per liter. Okay, so it's a measure of the relative capacity of a molecule. Okay, it's the only concentration unit that's reaction dependent, reaction dependent. Therefore, we'd have to write the reaction to actually write the compounds and see what's going on. basically we say, like this example right here, the molarity is times the number of H's in this case. So 1 molar sulfuric acid is 2 normal, because each mole of sulfuric acid provides 2 moles of hydrogen, while 1 mole of sulfuric acid is 1 normal for sulfate precipitation, what precipitates out. It's based on the subscript given. So since 1 mole of H2 of sulfuric acid provides 1 mole of sulfate ions, it's a 1 normal sulfate. It's based on how it precipitates out when it dissolves in water, how it's pulled apart by water. It's based on the subscripts that it provides. So there's normality. The way I describe it normally is that's normally about acids, and so it's based on the number of hydrogens multiplied. That's the most common application for normality. So the dissolving process video is brought up here again for you to look at it. We had some work time once again on that Monday, Tuesday of day 3 and 4 of solutions. And then I made days 5 and 6 be basically review and more practice problems. I facilitate a lot of practice problems, some of the more difficult multi-step practice problems that really challenge the participant in any way. So I do a lot of practice problems with the class, and of course you have plenty of time to work otherwise after that. So a lot of stuff going on there, a lot of problems being solved in those days, and lots of opportunity to grow. Nevertheless, this is the image for solvation again. Let's continue through the slides. Basically, we're through these are some old standards. Let's go through the other standards. Glassware, we don't really touch on these anymore because it's kind of an old news type of thing. So I'm just going to breeze through them. You're welcome to go back and look at those slides. They're interesting because we use different glassware based on what we're trying to do, especially for measuring and preparing fluids. Because certain beakers have different precision on them based on how they're made, we end up wanting to use certain glassware for certain purposes. Normally beakers are going to be just for collecting a sample, not necessarily for being precise in measuring amounts. Okay, we use volumetric flasks or graduated cylinders for that. Okay, wash bottle. So how do you mix a standard amount? You add your weight of amount of solute. You add wash bottle or a liquid amount up to the line that you want to, the line of the volume you want to achieve, and that's how you get it. Because you want to add enough water, not the solution amount of water. You want to add enough water to reach the total solution volume. Okay. Same thing with liquids. You put the liquid in first of the solute. You add your liquid solvent up to the amount to get to the amount of solution prepared. The way we would prepare solutions, one way to do it is to calculate it ahead of time so we know how much to add. And the way we do that is through what's called dilution. So when we talk about solutions concentration, you want to decrease the solution concentration, you would say you dilute it, right? So more concentrated, the opposite of that would be dilute. So we just take if we take a pitcher of orange juice and we start with this frozen Minute Maid bit, we would take this hunk of frozen lemonade, orange juice, let it thaw out, of course, and we'd add water, a certain volume of water, to dilute it to a new volume total with a different concentration or molarity. So we would take the molarity of the concentrated stuff, we take its certain volume of it, add enough volume to get a brand new volume, whose new volume would have a new molarity. M1V1 equals M2V2 is the formula gleaned from there. At first, this may seem complicated, but ultimately, you are given 3 out of these 4 numbers in a word problem. Your biggest task is to identify which M's and V's go together. Normally, what separates them is of. Certain amount of this molarity, or a molarity with this many liters. Anyway, they're usually easy to identify which M's and V's go together. Once you put them together, it doesn't matter which one you call 1, which one you call 2, as long as you identify the M's and the V's appropriately together. So for this example, okay, 2.5 liters of 4 molar CaSO4 solution, calcium sulfate, What volume of 2 molar can I make? So notice 2.5 and 4 go together. Let's call those M1 and V1 because they appear first. What volume? That would be a second volume if it were told to us. But we don't know, so that's V2. There's a question mark. Second molarity mentioned is 2 molar. That is of that volume. So those go together. And we list them. We plug them into our equation, M1 V1 or M1 times V1 equals M2 times V2. Leave the variable you don't know, as is the standard protocol for solving any equation at all. And solve for the variable you don't have, and you get 5, of course, 5 liters. Make sure we include our units in it. 5 liters. And that's actually the correct number of cichlids too. Let's look at another one. I want to make 0.75 liters of solution. It looks like the first volume mentioned. There's no molarity to speak of. So it's probably a missing. And it says using 0.25 liters, another volume, and a concentrated 12.12 molar. That's an M that goes with that V. This particular problem, or this particular strategy, involves just the first set that is together, we call M1 and V1. So 12 molar goes with 0.25 liters because they're talking about each other, right? They're connected by the word of, especially. We're going to call those, because those are the first ones that go together, the M1 and the V1. Whereas M2 is unknown, it's being asked about, and V2 is given as 0.75. Plug it in the M1 V1 equals M2 V2. Solve for M2, and it's 4 molar is the answer. Pretty easy, pretty straightforward. Lots of problems. I'm just going to click through this next one right here. We have, let me move me out of the way though. 3 liters and 6 molars. Those go together. 12 liters and M2. Good job. What volume of 12 molar? It would seem like there's a missing volume that goes with 12 molar. 1 liter and 2 molar. Once again, this strategy automatically puts the ones where there's an M and V that are known. It automatically makes those V1, M1. That's not required. I could have called 1 liter and 2 molar M2 and V2. I just want to make sure those go together. That's the most key point to it. 0.17 liters. Pause and take a look at that. Go back and look if you'd like, and just mute me. So we have more practice on dilutions in the worksheet. Let me show you that worksheet. We have dilutions. No. All right, so we end up coming to, before dilutions, we have this molarity practice worksheet. We do some molarity practice, which is briefly mentioned in the other video. Of course, missing sound, so I'm going to voice it over later. More molarity, more molarity, more molarity, more molarity. And that gives us, that's printed 2 to a page, front to back. So that's the first 4 pages are all considered molarity until we get to page 5, which dives into molality and the process of molality. Feel free to pause through on this and walk through molality on your own. Of course, these sheets are attached. So we get to page 6 and we get to some concentration problems of various sorts and pulling numbers out. I'm going to walk through a couple of these solutions later on in a separate video though, so don't expect it at the end of this one. But I will post, even if I don't get a chance to actually walk you through these, I'm going to post some of these answers that I've done on the board, on the smart board behind me, so you can have them to look at least look at them, and I'll explain them in more stepwise fashion later. All right, and we're on to dilution questions. And these dilution questions is where we practice our dilution math in a little greater detail. So at the end of this practice, of course, using the other formulas is also key, especially molality, especially the ones required in there. You're just going to refer, you list your numbers, make sure you identify what's the solute solvent amounts, convert or move decimals, whatever, to make them fit in the equations that are already listed, molality, mole fraction, percent composition, those different ones. See the separate picture I posted on Google Classroom for more reference. And then dilutions are there as well. Work on those practice problems, and we'll go from there. So basically from there, we just did a ton more practice problems in class. And that's really the furthest extent of it. Now, if I go here, there's another concentration set that I've actually pared down a good bit. And here is the modified version. I've attached this. I think I attached it to Google Classroom. More on that. I'll check on that in a second. But mostly I pared this down. There are a couple of added problems that I need to remove from this list to indicate that you don't need to do from these problems. I marked them off in class, and you could talk with a peer, and they'll tell you which ones we don't need to do. The only one that's going to be different is going to be this number 10. Those of you with this short page, number 10, you do need to do. Not number 10 here. I believe it's actually on page 1. Number 10 on page 1. I've just consolidated 10 and 11 into one problem. That's that number 10 there for this shorthand version. So that doesn't apply to you. You do need to do this problem, even though the other students have marked off number 10. Okay, so this gives us some more practice. It's greater depth. It's pretty difficult too. So don't be afraid to reach out. I'll give you a little tutorial on a lot of these things. I'm actually more helpful on these ones because they are so much more in depth. Look for the slides. I've answered a ton of these questions already. So look for the slides I'm going to post also, having worked these out. And they'll be stepwise. They pull parts out of the problem. You can go through at your own pace, scroll through like a PDF, and it reveals one step at a time. So make sure you please go look at those tutorials. If you need me to explain where I got and what I did with some of these numbers, please, by all means, let me know, and I'll give you a little voiceover, maybe a little voice memo, or I can break it down a separate way or just indicate a few things. Let me know what you're thinking so we can have an open line of communication. Bottom line is just a lot of these calculation stuff. The rest of this unit is just this work days of majority of the unit there is just working on solving concentration calculations and things like that. I'm a little off center here. I don't know what happened. Anyway, so the majority of that is just more practice problems. And then I basically recapped it on day 6. Day 6 was the day before the test, and I capped off some things on here. So a couple things. First, here we've got solution components, solute, solvent, which one does the dissolving, which one gets dissolved, right? Solute is dissolved, solvent does the dissolving. Vocab like soluble is the ability to be dissolved. Insoluble would be not able to be dissolved. The example I use is that like salt is soluble in water. Sugar is partially soluble in water. And starch, like from potatoes, is insoluble in water. It will settle out the bottom, might suspend for a minute. In terms for solubility for liquids would be miscible and immiscible. So you would say like ethyl alcohol or isopropyl alcohol and water are miscible. They mix together, like mixable almost, but a stranger word. And then immiscible. It's like oil and water do not mix, so they'd be considered immiscible. Some other vocab. Let me show you those right here. Solubility, ability of a solute to dissolve in a solvent. Solute, substance that dissolves in or is dissolved in a solution. Solvent, the substance that does the dissolving. Solvation is the process of the solute dissolving in a solvent, or the solvent pulling the solute apart. Dissociation would be the counterpart, solute being pulled apart by the solvent. So dissociation is more of a passive thing, and solvent is more of the aggressor in this case. Saturated solution with a maximum amount of solute, that means it's on the curve itself. Unsaturated solution with less than the maximum, that means the amount of dissolved solute is less than what is on the curve. Supersaturated is a solution with more than the amount, the maximum, more than what's on the curve is dissolved. It's above the solubility curve. Insoluble when two substances do not dissolve. Polar, nonpolar, dissociation, solution, other words to pay attention to. If you look at the review itself, which I'll post also to the Google Classroom, and if you look at that review itself, all right, that review will be posted there as well, and it will has a vocab section which is worthwhile and worth looking at. I'm going to post it to this video set just so you can kind of follow along from there. Cool. Oops. And that walks us through all the steps. Colligative properties would be the last little bit. We look at a colligative property lab. Idea is essentially that colligative properties is a property that describes how. Ooh, I also need to put those notes on the slide as well. Colligative properties are special features of substances that when solute is dissolved, it alters how that feature of the substance is acts, right? So water is the solvent. Its normal freezing point is 0 degrees Celsius. Its normal boiling point is 100 degrees Celsius. Those are two things that are subject to colligative properties, meaning when solute is added and the concentration increases of the water solution, where water is the solvent, that causes its boiling point to increase, or boiling point elevation, above 100, and it causes the solution made with water freezing point to decrease. So kind of like the mouth of a crocodile widening out. Okay, let's see. So bottom line are these features here, is that when salt is added to ice, freezing point decreases. When salt is added to water, boiling point increases. These were some lab demos I did actually on the ice cream day 4 of class. Prior to doing the ice cream, we just didn't have time or the lab equipment, temperature thermometers to actually see this. But salt added to ice, freezing point goes down. Salt added to water, boiling point goes up. Kind of like this. Boiling point elevation, freezing point depression are the two colligative properties we studied. There are 4 that we could study, but the other ones are trivial to us. I actually have a set of notes that I'm going to upload as well to the slides. I have some handwritten stuff to it, so I need to upload that specific picture. So stay tuned for that as well. Look for it on colligative notes. I handed those out as a handout, so that'll come soon too. The consequences of this change in boiling point, or the change of temperature, gives us the equation change in temperature of boiling point equals a constant times a concentration. This concentration is the number of the rate of molality. So for whatever reason, molality is what is impacting and what impacts the temperature, is what was decided upon. I don't know how it was decided upon, but it was nevertheless. So the way we calculate the temperature change due to the solute concentration increasing, the way we would account for it is calculate the molality of the solute, multiply times a constant, which must be given, to find the change in temperature. The change is changed to the change on the original solvent's boiling point. Since water is the most common original solvent, then we're talking about the boiling point changing according to 100 degrees C. So it'd be added to 100 degrees Celsius. Is how the molality changing, the molality concentration increasing, makes a positive change above 100. Delta TB, change in the boiling point. KB, molal boiling point constant. Look it up. Molality, moles of solute per kilogram of solvent. Same equation for freezing point, but this time it makes freezing point depress, go downward. And we leverage this idea by adding rock salt to ice and putting cream and milk and sugar and stuff like that in a plastic bag, putting it in the bag with ice and rock salt. And the rock salt changed the solute concentration of the ice, which made the concentration go up. So the delta TF went up, so that the freezing point of the ice was below 0, meaning it melted because the ice was at 0 degrees. The salt adding on makes the boiling or the freezing point be less than 0. So it was no longer at 0. It would start to melt. As it melted, melting by nature is an absorption of heat process. So it absorbed heat from the bag of cream and such. By absorbing heat, it's basically releasing cold or making it colder inside the cream bag, making the ice cream thicken. So here are our results. So let's see how this works. All right, and finally back to this. We talk about solubility curves. Got to be able to read those and interpret those, just like the activities we did. We kind of crushed that early on. Concentration calculations, that's your molarity, molality, mole fraction, percent. Those are in various degrees on the exam as well. Okay, and some mentions as well, multiple choice. We're going to do those. We practice those a lot. We have a lot of practice for them. So obviously they're going to be worth a lot more. Solvation and dissociation process is one of the essays, and colligative properties is the other essays, and one of the other essays. I go over this in class, but essentially the solvation dissociation process, I tell you to memorize that process from the video, whereby you talk about the positive end of a solvent attacks the negative end of a solute, pulls it away from it, the crystal structure, surrounds it with other positive ended solvents, and then it's dissolved, that component. Then the negative end of the solvent attacks the positive ends of the solute, pulls it away, surrounds it with other negative ends of the solvent, and that particle is dissolved. The process repeats until the solute is totally dissociated, broken apart, and completely dissipated. Then we have to talk about that in terms of factors affecting the rate. I forgot to list that up here as well. The factors that affect the rate of solubility, basically that agitation and increased temperature, increased molecular motion, so solvent works faster at dissolving the solute. Essentially marrying those concepts in there. So making smaller solute particles increases surface area, so solvent can get to more of the solute at an easier rate, so it moves faster because of an increase of surface area. And the colligative properties essay deals with talk about how molality affects colligative properties. Basically, molality is a specific type of concentration. So increased concentration means an increase in molality. More molality means more solute, which causes the temperature to elevate if boiling point, depress if freezing point. Those features being able to change based on the solute concentration are called colligative properties. So more molality, more change in either direction. That is how molality affects it. It's the concentration of it. And you need to discuss it in terms of maybe ice cream or some other example, maybe salt put on the roads of icy parts of roads or sidewalks and whatnot, or in terms of makes ice melt because it's going to be the freezing point changes. Anyway, bottom line, there are your essays. 49 represents 49 sentences that you can accomplish that in. 4 is no minimum, and 9 is not a maximum. 3 is not a minimum or maximum. 7 is not a maximum for colligative properties 1, but you could accomplish it with 3 great sentences and 4 great sentences. But they have to be great and just chock full of information. Anyway, that's it. That's the unit. Look for more practice problems posted, at least the slides posted from the class. Thanks for sticking with it. This is a long video, so if you stuck with it, you ought to be proud of that. And it was after a long day of teaching and working hard. This was on day 6 of class. Tomorrow is the exam for me and those who've been present. For those who not, we're going to arrange a different exam day for you. We'll figure that out at a different time. Keep up the good work. Send me your questions. Work on those worksheets. You know which ones I'm talking about. These ones right here. Oops, sorry, that got me zoomed in a lot. Work on those worksheets. Get them done. Get them together. And once again, this has been Night Chemistry, and this is Solutions number 2. Long video. Look out for more. Maybe even have another video of me working through some problems to explain my process that I show you on the slides. Good job. Go Dogs, and we'll see you next time. Y'all have a good night.